So today we're going to study this concept called theoretical probability. Now, we studied before experimental probability, right? And experimental probability was determined by using the results of an experiment, by calculating the probability of the event being the number of successful trials divided by the number of total trials. So the number of things that we want divided by the total number of times that we were testing for all of the possibilities. Now, when we're talking about theoretical probability, we're using analysis of possible outcomes by doing this. We figure out the number of possible successful outcomes theoretically, and then we divide by the total number of theoretical possible outcomes. So let's imagine that we have this possible scenario. We have Abe, Cecil, and Bruno. Each have won a prize, right, from Axe body spray for being smelly. The body sprays are shock, recovery, and fever. S for shock, R for recovery, and F for fever. It's just going to be randomly assigned to the three winners. So basically, they've just got a bag, and they're just going to pull out one and give one to Abe, pull out one, give one to Bruno, pull out one, give one to Cecil. Or they just give a whole bunch of stuff to Abe, and then a whole bunch of stuff to Cecil, and then a whole bunch of stuff to Bruno. And here is what the distribution of all of the different types of Axe body spray came out to be. So after giving out all this stuff to Abe, Bruno, and Cecil, this is what we have for the distribution of all of the Axe sprays. Now, I could ask you, by looking at the overall thing here, what is the probability that we have Bruno will receive fever? So Bruno receives fever body spray here and here. Okay, so P of fever for Bruno is going to be this 2 divided by, well, if you look at this, there are actually 1, 2, 3, 4, 5, 6 possibilities. Okay, so there's 2 choices out of 6. And then what we're going to do is we're going to simplify our little ratio or fraction to become the following answer, 1/3 as our final answer. So you could say the probability of Bruno getting fever is 1/3. And you'll notice that I said that it's a probability, and the probability is 1/3, right? I could have written that as a percentage or as a decimal, all of which would be perfect for the answer. But for us, right now, I'm just using fractions. So now, the next question I'd like you to consider is, how could you calculate the experimental probability that Bruno will receive the fever? Okay, so the experimental probability is the number of trials divided by the total number of trials. So I think what we'd have to do is we'd have to look at the distribution of Bruno, right? And imagine that there was a whole bunch of different experiments, like a whole bunch of trials where he gets different things from Axe. So instead of just having 6, maybe he has 1,000. And we go and look through and just keep track of all the fevers that come through. And that's it. That'll help us find out the number of fevers. All right. And now let's move on to our next concept of the day. This time we have a standard deck of playing cards, right? And this thing here represents all the possibilities of all the cards. We have ace, king all the way down to a 2 of hearts. And the same for clubs, diamonds, and spades. Now, in that case, when you count them, you're going to find out that there are 52 cards available to anyone that goes and plays cards. So each suit, a suit is every different type of card, whether it be hearts, clubs, diamonds, hearts, clubs, diamonds, or spades. Now, each suit has 13 cards. Now, if one card is drawn from the deck, then we need to find the probability of each event. So what's the probability of having a club? Now, if you think about it, this is what we call the theoretical probability, because we have our possibilities all laid out in front of us, and all we have to do is count the things that we're looking for. In this case, we're actually looking at if we're looking for clubs, this set of information here represents all the clubs that we have, right? So we would say the probability of clubs is some fraction, right? Now that fraction that we have has to be the number of clubs that we have in our complete set. So the number of clubs in our complete set is 13. And the total possibilities are 52. So now what I would tell you to do is I would take a look at 13 and 52. And I'll tell you right away that 13 can be divided by 13, and so can 52. It can also be divided by 13. And that gives us this fraction for our final answer, 1 over 4. So the probability of clubs is 1/4. And I could also change that into a decimal if I want, or a percentage. And either one of them would be fine. So let's just leave these as fractions for now. And now the probability of a king. So remember, the theoretical probability is to find all the kings, count them. And in this case, we have 1, 2, 3, 4 kings. And our total number of possibilities is 52. So now 4 and 52 can both be divided by 4. And we end with 1 over 13 as our final answer. So now let's go and try to find this next possibility for question C. When we're looking for a red card or a 2, we have to consider what or means in mathematics. Or when we're talking about stuff like this, the set of information, we're actually talking about the addition of 2 possibilities. So the red or a red card or a 2. So if I want to find all the possibilities of a red or a 2, we do something like this. And the possibility of a red or a 2 is equal to some fraction, right? Now, for the red, so you'd look and you'd count the number of reds, and in this case, I have 2 blocks of 13 red cards. And in that case, you're going to say that we have a possibility of 26, because 13 plus 13 is 26. And, or means plus. And what we're going to do is we're going to add the number of 2s in this, or a 2. So here's the rule. When you're looking at this, our reds were here and here, right? Now that we have those there and there, the issue would be, okay, so yes, I have those points, right? But then I'm also looking for all of my 2s. And you'll notice that your 2s will overlap with the hearts. So we're not going to count these 2s in our greens for 2. okay? So we're not going to count those 2 in there. So we're really only going to add 2 more because 2 of them are already counted in the 26. So it's 26 divided by 52. The total is 58. No, 28 divided by 52. And simplifying, divide the top and bottom by 4. So you end up with 7 over 13 as our final answer for our probability. Okay, so now ask yourself, how are we going to deal with a spade or a face card? So in this case, to find a spade or a face card, we have to look at all the spades. So there are a total of 13 of them. So we've got 13 plus. Now, we already have 3 sets of face cards right here. We can get rid of them. Okay, we don't need those, but you'll notice that we have 9 more face cards that we have to add to that set of things that we're looking for. So we're going to add 9 more cards, and then we divide that by 52, and then we add, and then we end up with 22 over 52. Now 22 over 52 can both be divided by 2, which gives us a final answer of 11 over 26 as our final answer. And so now let's take a look at playing any suit. So in this case, we have a heart, we have a club, a spade, or a diamond. So if we played any suit, we're going to have the following. Well, a heart is 13, plus a club is 13 possibilities, plus 13 again, plus 13 again. And you know what's really cool about it? None of them overlap, so we don't have to subtract any bits. So this ends up being 13 all over 52, which means it's 52 over 52. Wait a second. That's equal to 1, which is actually 100%. Oh boy. So the possibility of getting any suit is 100%. That makes sense, doesn't it? All right, let's move on to the next concept. Well, for example, 3 for today, right? We have Ferd. Ferd has won $100 on a game show, and Ferd has 2 options. He either keeps the $100 or risks $100 to possibly win $1,000. Okay? Now, if he rolls doubles with a 2-sided dice, so the key is he wins $1,000, he keeps $100, and then he risks it to see if he gets $1,000 if he gets a doubles. So imagine we wanted to go and show what this looks like in the real world. Now, in order to kind of understand what's happening here, we have 2 levels. We have the first die and then the second die. Now, so imagine if the first die roll gives us a 1, right? Now, to get to the second roll, there are 6 possibilities, aren't there? There is 1, 2, 3, 4, 5, and a 6th possibility. And imagine if I got 2 1s. Boom, shakalaka, I have just won $1,000. Now, this is what we call a tree diagram, okay? Now, a tree diagram or a table helps us understand how this works, right? So imagine the first row, in the first die, I get a 2. And then the second die has 6 possibilities again. 1, 2, 3, 4, 5, 6. Oh, I added one too many. 6 possibilities. And all we're going to do is we're going to imagine that we got a second 2. Holy jeez. We've made some money. Right? We've made some money. Now, imagine we do this ad infinitum from with all of 3s and 4s and 5s and 6s. We'll get something that looks like this. And those are the possibilities. Now, based on these nice trees, so remember the first row represented what would happen when we had our first die. The second row represented all the possibilities of the second die being rolled, right? So in the first possibility, imagine I got a 1. Then I had all these other possibilities, 1 through 6. And then I circled the matching ones from 1 and 1. Now that represents all that information. Now, here's the cool part. Now I could actually look at all this information. And I could tell you that my possibility of getting a doubles in order to make that $1,000 money that we were talking about earlier is going to be calculated by figuring out what we want, happening, divided by the number of leaves in the tree. So these things at the bottom of each one of these structures is called a leaf. And you'll notice there are 6 different blocks of 6, right? So for the total number of leaves, we have 36 leaves. Now what we want, how many times did that happen? That came up exactly once, twice, thrice, 4, 5, and 6 times. Now that I have that, I'm going to take that information and I'm going to take that fraction and reduce it right away. You'll notice that anytime I give you fractions for your probability, I want you to always reduce your fractions. So 6 divided by 6 gives us a 1. 36 divided by 6 gives us 1/6. So our probability of getting this information right is 1/6, right? The total possibility of getting a doubles from a tree diagram is that. So this was an example of a tree. Now, what do you think a table would look like? Let me help you with that. So this is what a table for dice would look like. So just humor me here. So what you're going to do is you're going to draw something that looks like this, right? And then you're going to put the numbers 1, 2, 3, 4, 5, and 6 along the bottom. This represents the first die. And then the stuff going along the vertical axis represents the second die. And now, here is the best part. In order to fill this information, all we have to do is add 1 and 1. What's 1 and 1? 2. What's 1 plus 2? 3. 4, 5, 6, 7. And now, imagine we want to figure out what 1 and 2 is. So the sum of 1 and 2 is 3, isn't it? And then 2 and 2 is 4. And guess what? We can follow the pattern across. But make sure you keep these numbers aligned vertically and horizontally. So what's 1 plus 3? We got 4. The next number is 5, 6, 7, 8, 9, and you continue. Now, that's what we get. We get this amazing little table that basically shows all of the possibilities, all sums of 2 dice. So now, what's the probability for this probability sum table? So the probability sum table that we have here is amazing, because now all I have to do is look for doubles. One doubles is a 2, another doubles is a 4, a 6, an 8, a 10, and a 12, because 1 and 1 is a double, 2 and 2 is a double, 3 and 3 is a double, and I can find that in my chart. And so now I can easily see what we have here. The probability of doubles is equal to, well, it's still 6, because there's only 6 red selections, divided by 36 points in my set. And the final answer is still going to be 1 over 6. I'm very happy with this. So remember, that dice sum table that we have here, that we have right here, is one of the most useful things that you can do when you have to go and figure out all the different possibilities of 2 dice. And this is why we love theoretical probabilities. Now, so here is method 2. Okay, method 2 involves us thinking about how we could work this problem a lot easier. The problem is dumb. A problem comes out by doing this. Okay, so think of the probability of doubles happening, right? We can think of it as the probability that the second die is the first. Isn't that what our trees are saying? The first die and the second die are the same. The first die is chosen, and then we get the second die. Let's go and see what happens here. Think of a dice when it rolls, right? When a dice rolls, right, there's 2 possibilities. We have the first die and the second die happening. And anytime you hear about ands happening, we're talking about multiplication. Now, what's the probability of the first die? So when the first die rolls, it has a 1 in 6 chance of getting something, right? The second die has no choice but to be the same. So the first choice is 1 over 6. The second die is 1 over 1. 1 times 1 on the top is 1. 1 times 6 on the bottom is 6. Isn't that what we said our probabilities were? So the probability of getting the second die being the first die is 1/6 for the first die. So when you roll the first die, you have a choice of 1. You have a choice, 1 in 6 chance of getting a number. But then the second die must match. Second matches. So it's a 1 in 1. It's a 1 out of 1 possibility. There's no choice, right? That's why it works. And then you just multiply them together because they both happen, one right after the other. One depends on the other. So here is our homework for today. You're going to be doing page 73, number 1, 3, 5, 6, 8, 9, 10, and 12. Now these last 4, 7, 11, 13, and 14 are challenging. These ones These ones I want you to try. You don't have to get them, but I just want you to try them. You don't have to get them, but I just want you to try them. Thank you very much. Now have a good day. You will have homework for this one.